hanging in there, especially those of you who are very jet lagged. And of course, giving a talk to this audience would always be special, but of course, but at KIST as part of this workshop is even more so. And so today I thought I would tell you about some work we've been doing on recycling, but I did at the last minute some work on fibers because I like to classify CNT materials as fillers, sheets, and fibers. And what I'll show today is some work on sheets, and then later on fibers. And the idea is, if you think of these as some sort of nanomeric materials that you can assemble into different formats, then if you look at the volume fraction, that really dictates whether you are in the working with additives or sheets where they have predominantly, well, some degree of alignment through the thickness, but randomly in the plane, as you can see here, or aligned fibers and fabrics. And so really it's about alignment and mass fraction that takes you through all these length scales. Now, recently we were invited by a colleague to put together a book chapter on what we think will be the future of CNTs on a very large scale. So thinking, for instance, about the carbon hole objectives. And of course, so one of the things I wanted to do was to try to estimate where this will be in, say, 3-10 years' time. Now, for additives, so for fillers, that's relatively easy because you just have to look at how much LG is going to produce, and then that's straightforward. So my guess was about 5,000 tons, which is not too far, and then it will go up to 20,000. So that's not too bad. But when I look at the development of sheets, I think that's actually very promising, and that's speeding up a lot. And I see three main applications that are close to being ready for industrialization. One is, of course, EMI shielding. So this is from Adam Boyce's lab together with Tortec. And another one is de-icing and dew heating. I think that's quite promising for wind power. And I think there's space for sheets in wind power, also for interlaminar reinforcement. And the third one is current collectors. We've done some work on current collectors. So I see those as very interesting applications. If you think of, well, if those were initially industrialized, and even at a small scale, we would need about 1,000 tons, I reckon, of those, and that would grow to 10,000 pretty quickly. And that would not be, of course, a full market for these applications. And of course, and CNT fibers, that's a hard guess for me, because I was thinking more of conductors, but even that will need several tons to start demonstrating prototypes, and that will increase quite fast. So when we put together these numbers, we thought, well, we really should start looking about recycling, and that's the first part of my talk. So what will this recycle like, and particularly sheets? So I'm not thinking of fillers. Now, this is because we want to learn from past mistakes, and this is, for instance, the volume of carbon fiber composites, and this is on the hundreds of tons kilotons per year. And that's going to catch up with us in about 5-10 years' time, and we're going to have to recycle all that carbon fiber. That's a huge challenge. So, just to give you a feel for what that looks like in terms of components. So there's about 35 million vehicles in North America, around the world that are recycled every year, and we're going to have tens of thousands of aircraft coming out of service pretty soon. And the trouble is, a lot of that carbon fiber goes in a landfill, or it's not particularly used. So of course, in Europe and other places, the view is new materials or components need to be recyclable by design. So that's something I believe we need to work on. So for this particular work, we've used two types of CNT sheets. One produced in my lab, you've seen this before, so it's floating catalyst CVD. And we also used some material from Nanocom Huntsman and from Tortec, because we wanted this to be relevant for everyone and not just specific to our material. And there are other reasons why this was particularly useful. Now we used the sheets in there only because we could align them, and of course that's well known to produce much better properties. So we could do some alignment by control of the drawing process of the aerogel or through wet processing. So this is an example of wet drawing, and you can see that with little force you can draw these materials. Now that's good because it means that you can get decent properties in sheets. So this is about 1.2 Newton per tex in a wet drawn material, and this is 50 Newton per tex modulus in wet drawing. And that's also particularly interesting for me because I think if you can align sheets, you have a fabric, an aligned fabric. You actually never have to make a fiber in the first place. So we've done some micromechanical studies, and these aligned fabrics behave essentially as sheets. So the orientation parameter is high enough that you can treat them as align fibers. So to do this recycling study, we produced the largest composites we could with the material available. So these are sort of 10 by 10 sheets, and we infused them with commercial thermosets. So this was, for most of these studies, we use an epoxy from Hexel, which is an aerospace grade epoxy. This is infiltrated, and we need to apply a bit of pressure for this to infiltrate, and then we cure it with a vacuum bag. So this is about as industrial as we can go with the format of the materials we have at the moment. But these are recognized as reasonably, reproducible composite processing methods. So there's not much porosity and so on. And so the idea is we make a composite, and to study recycling potential, we produce these composites, we cure them, then we pyrolyze the matrix, oxidize it slightly, and then evaluate the properties. Now, of course, you could recycle in many other ways, and I'm sure there are many better ways of extracting the polymer. We didn't do it because our interest was in understanding how the CNTs survive the process. And this recipe, I suspect, could be improved significantly. We just took it from some colleagues who are working on recycling carbon fibers. Now, the key is if you apply this annealing, this thermal process to carbon fiber composite, essentially it gets all fluffy and it falls apart. So that's a big problem because you lose a fabric. You have something that is much more like discontinuous filaments, and that's very difficult to mitigate later because you have to realign them and so on. There's a whole effort around the world in trying to prevent that and to mitigate it, but that's intrinsically pretty hard. So this is what we did. This is an example, for instance, of a prepreg from Huntsman, and then to demonstrate how you can process these, we thought, let's make a little paper plane. Now this is fully cured, so this was folded and cured, full curing temperature, 180 degrees, 2 hours, and so on. And after curing and removing the polymer, we could unfold the sheet completely, and it's still flexible. This is folding it 7 times over itself. Now, you'll notice that there's some tin foil. That's just so that the resin doesn't stick to itself and we can unfold it. So this would be freestanding without tin foil, so it's not cheating. So that for us was quite impressive because you look at the sheet and it does preserve that fabric structure, which means that it has a huge value compared to what you would obtain with monolithic fibers. Of course, if you look at it under the microscope, it looks the same. And here's some Raman spectra for Professor Maruyama. So you will see that the Raman spectra are nearly the same, and I'll show you that statistically they are within the same, so there's little differences. And we looked at their tensile properties, and they are slightly different, but close to 80% tensile strength. The modulus in fact increases, so this is perfectly processable, and it looks very similar. We also tried our our Moreline material. Again, it looks the same under SEM, and the Raman spectra looks identical, so there is little difference. Statistically, they are the same pretty much. We saw a tiny drop in strength, and that's because the sheets we produce at Indea are way thinner. They're about 2 grams per square meter, which means that they're very hard to manipulate. The commercial ones are 12 to 14 grams per meter square. Now let me walk you through the properties in this table. So the strength is preserved up to 59% in our aligned ones and 95% in the commercial ones. The modulus in fact increases. That's also well known because you start to pyrolyze the amorphous carbon and so on. And the electrical conductivity remains essentially the same, which is pretty important if we're thinking of putting these in batteries or using them as current collectors or EMI shielding. And the Raman spectra looks the same. So that's pretty good because the result is the shape is preserved and most of the properties are retained after recycling. Now, something we've been dealing with is how do you compare with what you would achieve in carbon fiber? And I think the best way is to say, okay, let's compare apples and apples. So these are the properties of the fabrics, and these are the properties you would get with carbon fibers as a single filament. So a lot of researchers are working on looking at the properties of the filaments, but that's just a small short fiber filaments. That's not a fabric. You can make a tow, but even that tow is not particularly good. So in a comparison of sheets or fabrics, these materials really stand out compared to the carbon fiber fabrics that people have managed to remake from these short fibers. So that's great news, because it means that within the scale of recycling, we really are seeing the best possible scenario, which is something close to either reusing or recycling for the same application. So with carbon fibers, essentially one ends up losing value because they get short and they have to be either chemically recycled or used for a lower grade application. Now, we'd like to understand this in more detail, particularly to see if this will apply to higher grade fabrics or CNT sheets as they become more available. Now, the starting point is to realize that in a fabric of carbon fibers, of course, or any monolithic fibers, these are discontinuous elements. And on top of that, monolithic fibers are very brittle. Right? So for instance, you can do a very simple calculation, which is, what's the probability that a single filament would retain its strength? And if you see that for any component of, say, 100 millimeters, the probability is pretty small. So they will degrade significantly, and they will probably break. And in the process, you lose the shape because there's no connection between them. A CNT sheet is much more similar to a polymer sheet in the sense that it's a network that is connected between all the elements. So that's very important to keep the shape. And what we've been trying is to understand the mechanics of that system. So you can if you treat it as a polymer, and you have to, because in carbon fibers you would determine toughness through the fracture toughness, but that only applies to linear elastic materials. And we know that CNT sheets deform through a significant plastic deformation, so you cannot really determine the fracture toughness. Instead, what one normally does for these network materials is to make a notch of these different sizes. So you produce a ligament and then do a tensile test and see how the fracture energy changes for different ligament sizes. So we cut these using a laser cutting machine of with different ligament sizes. The ligament refers to the size that is unnotched, that we didn't cut, and this is what they look like under a tensile test. And these are the results. So these are the stress-strain curves, and for different ligament sizes. We tested quite a few of them for each ligament size, but only a few ligament sizes. And you find that these are self-similar, which is normally a good sign that they behave like a polymer or a ductile metal. And you of course see this plastic deformation and energy absorption after they have yielded. Now, the whole idea is that if you do this experiment, the principle is that when the material deforms, there'll be an inner fracture process zone, which is related to the intrinsic or the essential work of fracture, and that will be a thin line. So that will scale, that will depend on the length. And there'll be an outer area, the outer process dissipation zone, which may be really affected by the geometry of your sample. So that's how, for instance, ductile metals and plastics are analyzed. So it means that if you do this tensile test for different ligament lengths, you extrapolate to zero, you determine the essential work of fracture. So this is the simple equation describing that behavior. So you determine the essential work of fracture as the intercept, and you can also determine the plastic dissipation, which should be more geometry dependent. So how do CNT sheets compare to other materials? So this is a plot of the essential work of fracture, and then the plastic more geometric dependent parameter. So as you can see on this scale, this is for the commercial and this is for the one produced at Vilatela. So both have a very high essential work of fracture, so that's good. So it doesn't seem like we sacrifice fracture toughness by aligning. And this is well in the range of tough plastics and even some metals. So that really is very encouraging, and that helps understand why this material can handle recycling. Now, you can also think of another figure of merit, which is the strength against the essential work of fracture. So sorry, I've moved this axis to this side, and you can see, for instance, how they compare to some metals. So the strength is higher, of course, in normalized by density, but the essential work of refractory is pretty similar. So we are finding that these macromolecular structures have an inherent toughness. I mean, this was suspected, but now we're being able to quantify it better, and that is quite key for recycling. Now let me move on to a totally different topic, so I felt like I should talk about fibers as well. So I'll share some results on CNT fibers for sensors. And this is a simple problem, but one that has been bothering me for many years. I'm sure many of you have done this experiment where you take a fiber, you stretch it, and if you measure the electrical resistance, it increases as well, so that the material is intrinsically piezo-resistive. And you can calculate a gauge factor, which is the figure of merit for how sensitive it is, right? And it's just a relative change in resistance divided by the strain. And of course, people do all kinds of fun things with this, so we are also trying to see if this is useful for aerospace composites. So for instance, we take tows or thick fibers from commercial vendors, and then we have some colleagues, so we're part of a big consortium, and we have some colleagues in Galicia that are 3D printing printing a filament of CNT tows with PEEK, and they can make sort of 50 meters or so. We are looking at the piezo resistance because it increases slightly when you put the polymer phase inside. And of course, PEEK is chosen because it is the polymer for aerospace. And then we produce composite panels and then cut off some small coupons. So this is a composite panel with a fully embedded contacts. And you can see here a cross section. So these are carbon fibers. These are aerospace carbon fibers. And you can see here this film. Of course, there's a resin-rich area here, which is not too bad because it prevents any shorting between the two. And we seem to have very good infiltration of PEEK into these CNT fibers. So we put sensors, connect the cables, and the idea is, can we use this as a sensor? Of course, the answer is yes. We get a nice linear piezo-resistive signal, and we're working on trying to exploit that for simulation. So can we really start using this to detect damage and to simulate and so on? And truth be told, every now and again we get a bit of noise, and this is a challenge. We need to make them more reproducible, but I don't really see that as a big problem in the long run. Perhaps the biggest challenge is how do you localize damage and not just sense it, not just detect it. Right? But anyway, the problem that has been bothering me is, where does this piezo resistance come from? So a while ago we made some samples where we put filaments in. So we knew that the piezo-resistive coefficient was positive in tension. So we thought, well, what about compression? So we made samples with specimens for 3-point bending, one in tension, one in compression. So what you find is that actually all of it falls on a master curve. So this is just a normal tensile test, and then this is the specimen in tension in the 3-point bending experiment, and this is in the 3-point bending compression. And we see this U-shape consistently. So in other words, whether you compress the fiber or you stretch it, you still get a positive piezo resistance. So I asked my student, well, go and tap on the sample and see if you compress it transversely, right? So you go and press it with your finger, well, not your finger because you make it warm, but press it with something, and you also get a positive coefficient. So the piezo-resistive coefficient is positive irrespective of the deformation. So I thought, well, that's strange because, nanotubes cannot be sliding, and the classical models you have for networks would not explain this. So we went and played with some of the floating catalyst material, and we found that, first of all, the gauge factor increases more or less linearly with modulus. We then got some material from rice, which is much more uniform, and indeed, perfectly linear behavior. So, in other words, the stiffer the material, the higher the gauge factor. So the more you can transfer stress to it, the more the change in resistance. So that's more or less expected. I mean, what we're saying is the change in resistance is proportional to the stress transfer to the CNTs, right? So the piezo resistance is coming from the deformation of the CNTs, and that's important. So you don't see that when you make, low volume fraction filler composites. And what we've been trying to work out is, well, where does that come from? Now, if you look at the literature and what I think is the best understanding of piezo resistance in individual CNTs, right? So people have looked at that in detail, and essentially the idea is if you take a nanotube, and the resistance will depend on pretty much exclusively on the band gap, and that band gap will open as you stretch it, right? That's relatively well known. The trouble is that will only open, a band gap will open only if they are not armature, so only for certain chiral angles. So this is the prediction of piezo resistance, and you can see, for instance, this 1010 tube, no piezo resistance at all. So this predicts that only certain chiral angle single nanotubes would be piezo resistive. And that is for individual tubes. And we thought there was probably something else going on. So we tried a few more experiments. This is one. We took some rice fibers and varied the amount of dopant inside, and you find that if they have no dopant, if the dopant is more or less zero, the gauge factor is really very high, the highest we've tested for any fibers. But as soon as you start doping them, that actually drops linearly. So doping them is decreasing the piezoresistive factor. And it's not really, and at first it wasn't obvious to us, for us why. So the second insight we got into this came from other work on doping we did. And essentially we took a fiber or film and we did some low transfer measurements with and without dopants. And you know, this is, some people have observed this in the past. So you essentially, if there's no dopant, the material is a combination of a metallic resistance and a more semiconducting resistance. And if you dope it, you essentially suppress that semiconductor-like behavior. And it was more or less believed that the dopants would essentially increase carrier density, just like they do in a semiconductor. But I'm not so sure about that, because first of all, if you think of a real fiber, there are a lot of these tubes, and a lot of the conduction is probably through the junctions between them. So to test this hypothesis, we measure the transverse conductivity, and sure enough, the transverse conductivity also increases hugely after doping. So I guess what I'm saying is we need better models for the transporting these large systems. I think they need to include the junctions, which are not, in fluctuation induced tunneling, which is the most common model. You know, that's too simple for this complex system because we need resistances in parallel, not just in series. But anyway, so with that insight, what I think may be happening in piezo resistance is essentially that what we're seeing is the effect on the tunneling resistance. So if you take nanotubes that have no strain, so the Fermi level is probably close to here, and then if they are strained, a gap may perhaps open. But of course, the issue is that is the tunneling between the two tubes. In the case where the tubes are doped, where the Fermi level is pretty far, and therefore there's a high density of charges, even under strain, there will still be tunneling because there's a high number of states that the electrons can tunnel through. So I think it's in the tunneling resistance that is the piezoresistive effect. Now, of course, when we produce cartoons like this, it's always good to compare with something more real. So this is the simulation that others have done for the effect of strain on individual tubes, and you can see that, for instance, if you stretch them, say 4% to 3%, you do get these really large changes in the density of states. And the question is, how do they compare to the kind of doping we find? So, for instance, for the tubes, for the rice fibers we've been doping, we see typically Fermi level changes of about 0.5 electron volts. So it is possible that the Fermi level is somewhere here where strain is inducing huge changes in the density of states. So I guess I would encourage all the simulation experts to see if you can simulate some more realistic systems for us, like double-walled nanotubes, different chiralities, and understand these transport properties in the transverse direction, not just along the tubes. So with that, I finished just by summarizing, and then so hopefully I persuaded you that the CNTs are inherently tough, that this opens, I think, new possibilities for recycling, which I think is hugely critical. Now, the toughness we measure through essential work of fracture, which is a concept we're borrowing from polymers. And with respect to fibers, I think it's interesting to look into the transport properties and their piezo resistance. I believe it's coming largely from tunneling, and hopefully through more transport studies and simulation we can clarify that. And I thank my collaborators, colleagues, and of course the students who do the work and the various funding agencies. And thank you for your attention.
Thank you very much. So we have 3 minutes for discussion. So the questions? Yes.
Thanks, Juan. That's really interesting. Thinking about the possible mechanisms for the junction change. I mean, I remember some experiments done a while ago when they were indenting nanotubes on a substrate with an AFM tip. So there, it was not a tensile deformation along the axis. It was sort of creating an indent, and that was reducing the conductivity along the axis very substantially. Could it be that those kind of effects might be responsible?
The simulations predict that some chiral tubes should have a negative piezo resistance, but then you should see that even without dopants.
But I think that the mode of deformation, if I understood rightly from all your things, you were assuming some tensile deformation or compressive, but it was always along the axis of the tube.
Yeah.
Correct? So I think I'm thinking about a deformation perpendicular to that, and if you have tubes in a network and you press them, maybe they're getting squeezed down, and that's perhaps changing their conductivity.
So the experiment we did where we applied transverse compression increased resistance as well. I mean, it's not as controlled as the other ones, but if you do transverse compression, there is an increase in resistance as well. There's no decrease. So it doesn't look like what you're seeing is a change in the average gap between them.
Thanks.
Last piezo resistance discussion, can we just simply say, of course, you have to discuss band change, but if you have the tunneling probability, actually it is just easier to see some more scattering, like electron or hole can really go tunneling, mean they have some probability to have resistance in this way. So it could be even without thinking about the band gap change, or so it just tunneling, going to the transverse conductance is something resistance in the longitudinal direction is possible, or maybe I'm thinking that too simple.
I mean, what I can say is that the charge has to go from one tube to the other, because of course they are finite relative to the large sample. So that has to happen, or unless there is tunneling from one end of the tube to the other. But what we find, for instance, with doping is that the dopants do not change the average separation between the tubes. So they keep it the same.
Is there a question?